Hello, and welcome to this quiet corner of the universe where science meets wonder. I'm so glad you found your way here tonight. Whether you're settling into bed with the weight of the day slowly lifting from your shoulders, curling up on a familiar couch as evening light fades through your windows, or simply seeking a moment of peaceful contemplation, wherever you are in the world, you've arrived at exactly the right place. Before we begin this gentle journey into the quantum realm, I'd love to know where you're listening from tonight. Are you tucked beneath blankets in a bedroom overlooking city lights? Perhaps you're watching stars emerge through a window in the countryside. Or maybe you're somewhere entirely unexpected, letting these words wash over you like a soft tide. Wherever you are, take a moment to settle in. Get comfortable. This is your time. Now here's something that might surprise you. Right now, as you listen to these words, trillions upon trillions of particles are dancing through your body. They're not just passing through the space between your atoms, they're literally tunneling through barriers that should be impenetrable, existing in multiple places simultaneously, and somehow maintaining mysterious connections with particles on the other side of the galaxy. This isn't poetry or metaphor. This is the strange, beautiful reality of quantum physics. And here's the truly remarkable part. We've only just begun to understand how deeply weird the foundation of our universe really is. There's something profoundly humbling about quantum physics. For over a century now, it has stood as perhaps humanity's greatest intellectual achievement, explaining everything from why stars shine to how your smartphone processes information. Yet even today, even with all our sophisticated mathematics and experimental precision, quantum mechanics continues to reveal mysteries that challenge our most fundamental assumptions about reality itself. Picture this. You're holding a coin between your fingers. You flip it into the air and it spins gracefully before landing with a gentle clink. Heads. Simple enough, right? But what if I told you that, according to quantum mechanics, before you observed that result, the coin wasn't secretly heads or tails at all? It was genuinely, physically, both. Not just unknown to you, but existing in what physicists call a superposition of states, a shimmering blend of all possibilities until the moment you looked. This isn't just a thought experiment or a philosophical puzzle. This is how the universe actually works at its most fundamental level. And it gets stranger. In laboratories around the world, scientists routinely observe particles that seem to communicate instantaneously across vast distances, as if the very notion of space between them is meaningless. They watch as individual photons of light somehow pass through both slits in a barrier simultaneously, creating interference patterns that can only be explained if each particle literally takes every possible path at once. They measure electrons that tunnel through energy barriers they shouldn't classically be able to overcome, as if the laws of physics are more like gentle suggestions than rigid rules. The great physicist Richard Feynman once said, "I think I can safely say that nobody understands quantum mechanics." He meant it as both a joke and a profound truth. Even those who work with quantum equations every day, who build technologies from its predictions and push the boundaries of what's experimentally possible, will admit that quantum physics doesn't just challenge our intuitions about how the world works, it shatters them completely. And yet, there's something deeply beautiful in this strangeness, because what quantum physics reveals isn't chaos or meaninglessness. It reveals a universe that operates on principles so elegant, so precisely mathematical, and so consistently verified by experiment that it represents one of the most successful scientific frameworks in human history. It's just that these principles happen to be completely alien to our everyday experience. Let me share with you one of the most beautiful experiments in all of science. It's called the double-slit experiment, and it's so simple you could set it up on your kitchen table. Yet it reveals something so profound about the nature of reality that it continues to perplex physicists more than a century after its discovery. Imagine you have a flashlight, a piece of cardboard with two tiny slits cut into it, and a screen to catch the light that passes through. Shine the light through the slits, and you'll see a pattern on the screen. Not just two bright lines where you might expect, but a series of alternating bright and dark bands, an interference pattern that can only be created when waves overlap and either reinforce or cancel each other out. This makes perfect sense if light behaves like a wave, spreading out and interfering with itself. And for a long time, that's exactly how physicists understood light. But then something remarkable happened. Scientists found ways to turn down the intensity of their light source until it was firing just one photon at a time, individual particles of light making their way toward the slits one by one. Now you'd expect these lone particles to behave like tiny bullets, each one going through either the left slit or the right slit, eventually building up two bright spots on the screen. That's what particles should do, right? They should follow definite paths, exist in specific places, behave according to the common sense rules we observe in our daily lives. But that's not what happens. Not at all. Even when sent through one at a time, these individual photons gradually build up the same interference pattern as before. Somehow, each single particle appears to pass through both slits simultaneously, interfering with itself to create the wave-like pattern. It's as if each photon is exploring every possible path, every route through the experimental setup, all at the same time. But here's where it gets truly mysterious. The moment you try to peek behind the curtain, the moment you place detectors at the slits to see which path each photon actually takes, everything changes. The interference pattern vanishes completely. The photons start behaving like well-behaved particles again, each one going through just one slit or the other. The act of observation itself seems to fundamentally alter the nature of reality. Albert Einstein was deeply uncomfortable with quantum mechanics. This wasn't because he couldn't understand the mathematics, or because the experimental results were unclear. Einstein understood quantum theory better than almost anyone. His discomfort ran deeper, to the very foundations of what he believed reality should be. God does not play dice with the universe, he famously declared, expressing his belief that the fundamental laws of nature should be deterministic, predictable, and independent of whether anyone happens to be watching. Einstein wanted a universe that existed objectively, where particles had definite properties regardless of measurement, where the moon continued to exist even when no one was looking at it. But the quantum world seemed to suggest something far stranger. It proposed that particles don't have definite properties until they're measured, that reality itself might be fundamentally probabilistic rather than deterministic, and that the very act of observation plays a crucial role in determining what becomes real. Einstein spent decades trying to prove that quantum mechanics must be incomplete, that there had to be some deeper theory, some hidden variables that would restore the classical picture of reality he found so compelling. Along with his colleagues Boris Podolsky and Nathan Rosen, he devised thought experiments designed to show that quantum mechanics led to absurd conclusions. One of their most famous arguments involved what we now call quantum entanglement. They imagined pairs of particles that had interacted and then separated by vast distances. According to quantum mechanics, measuring one particle would instantaneously affect the state of its partner, no matter how far apart they were. This seemed to violate the principle of locality, the idea that objects can only be influenced by their immediate surroundings. Einstein called this spooky action at a distance, and he was convinced it proved that quantum mechanics couldn't be the whole story. There had to be some hidden mechanism, some deeper level of reality that would explain away this apparent instantaneous connection between distant particles. But Einstein was wrong, and the universe is far stranger than even he was willing to accept. In the decades following Einstein's death, physicists developed ways to test his ideas experimentally. They created pairs of entangled particles and measured their properties across increasingly large distances. What they found was both beautiful and unsettling. quantum entanglement is real. When two particles become entangled, they form a single quantum system, no matter how far apart they travel. Measure the spin of one particle, and you instantly know the spin of its partner. Not because they were carrying this information with them like hidden instructions, but because the act of measurement on one particle genuinely, physically, affects the state of the other. This doesn't mean information travels faster than light, which would violate relativity. The connection is more subtle than that. The entangled particles share what physicists call a quantum state, a mathematical description that encompasses both particles as parts of a single, non-local whole. When you measure one particle, you're not sending a signal to its partner. You're collapsing the shared wave function that describes both particles together. Recent experiments have demonstrated entanglement between particles separated by hundreds of miles, using satellites to beam entangled photons across continents. The results are always the same. The quantum correlations persist, the spooky connections remain intact, and our classical intuitions about how the world should work continue to crumble. But perhaps the most remarkable thing about quantum entanglement isn't just that it exists, it's that we're learning to use it. Quantum cryptography already employs entangled particles to create communication systems that are theoretically unhackable. Any attempt to eavesdrop on an entangled quantum message automatically disturbs the system, alerting the legitimate users to the security breach. Quantum computers harness entanglement to process information in ways that classical computers simply cannot match. Where a classical computer examines possibilities one at a time, a quantum computer can explore vast numbers of possibilities simultaneously, using the strange correlations between entangled quantum bits to solve certain problems exponentially faster than any classical approach. There's something deeply unsettling about the role that observation plays in quantum mechanics. It suggests that reality isn't quite as objective as we once believed, that the boundary between the observer and the observed is far blurrier than our everyday experience would suggest. When physicists talk about measurement in quantum mechanics, they're not just describing the act of looking at something with our eyes or detecting it with an instrument. They're describing any interaction that extracts information from a quantum system in a way that forces it to choose between its various possible states. Before measurement, a quantum particle exists in what's called a superposition, a mathematical combination of all its possible states. The particle isn't hiding its true state from us, waiting to be discovered. It genuinely exists in all possible states simultaneously, with different probabilities for each outcome. But the moment a measurement occurs, something dramatic happens. The superposition collapses. The wave function reduces to a single, definite state, and the particle suddenly has definite properties. This transition from many possibilities to one reality is called wave function collapse. And despite decades of research, no one fully understands how or why it happens. Some interpretations of quantum mechanics suggest that consciousness itself plays a fundamental role in this process, that the act of conscious observation is what causes the wave function to collapse. Others propose that any interaction with the environment, whether observed by a conscious being or not, is sufficient to cause collapse. Still others, like the many worlds interpretation, suggest that the wave function never collapses at all, that every possible outcome occurs in separate branches of reality. The measurement problem, as it's known, remains one of the deepest unsolved mysteries in physics. It strikes at the heart of fundamental questions about the nature of reality, the role of consciousness in the universe, and the relationship between the quantum and classical worlds. One of the most practically important quantum phenomena is also one of the most counterintuitive. It's called quantum tunneling, and it allows particles to pass through energy barriers that should be completely impenetrable according to classical physics. Imagine trying to roll a ball up and over a hill. If the ball doesn't have enough energy to reach the top, it will simply roll back down. classical physics tells us that's the end of the story. But in the quantum world, there's a small but non-zero probability that the ball could appear on the other side of the hill without ever going over the top. It doesn't smash through the barrier or find a secret passage, it simply materializes on the other side, as if the barrier weren't quite as solid as it appeared. This might sound like science fiction, but quantum tunneling is happening all around us, all the time. It's the reason radioactive atoms decay, allowing alpha particles to escape from atomic nuclei even though they don't have enough energy to overcome the nuclear binding forces. It's the mechanism that allows nuclear fusion to occur in the cores of stars, enabling hydrogen nuclei to merge and release the energy that makes starlight possible. Without quantum tunneling, the sun wouldn't shine. The nuclear reactions that power our star require temperatures and pressures even higher than those found in the solar core. But quantum tunneling provides a shortcut, allowing fusion reactions to occur at the relatively modest conditions found in stellar interiors. Quantum tunneling also underlies many modern technologies. Scanning tunneling microscopes use the quantum tunnel effect to create images of individual atoms on surfaces. Tunnel diodes exploit quantum tunneling to switch electronic signals faster than conventional devices. Even some theories of biological processes, like enzyme reactions and the sense of smell, invoke quantum tunneling to explain how certain molecular interactions can occur so efficiently. As we drift deeper into this quantum landscape, we begin to see that the strangeness isn't just an amusing curiosity. It's woven into the very fabric of existence, enabling the processes that make life, starlight, and consciousness possible. The universe isn't just stranger than we think, it's stranger than we can think, operating on principles so alien to our everyday experience that even our most creative imaginations struggle to grasp their full implications. And we've only just begun to explore the depths of quantum weirdness. There are phenomena yet to be discovered, mysteries yet to be unraveled, and questions about the nature of reality that we haven't even learned how to ask. As you rest tonight, perhaps you'll dream of particles dancing through dimensions we can't perceive, of realities branching and merging like streams of light in the darkness. And when you wake, you might find yourself wondering about the quantum processes occurring in your own consciousness, the tunneling electrons in your neural pathways, the entangled states that might connect your thoughts to the vast cosmos beyond. But that's a journey for another evening, another gentle exploration into the mysteries that surround us. Next time, we'll venture even further into the unknown, asking whether space itself might have an edge, a boundary, where everything simply ends. Does space end? Sleep documentary awaits whenever you're ready to continue this cosmic journey. Sweet dreams, fellow travellers. The quantum universe is dreaming too. There's a profound irony at the heart of quantum physics that might shift how you think about emptiness itself. We often imagine empty space as truly empty, a vast void where nothing exists, nothing happens, nothing stirs. But quantum mechanics whispers a different story entirely. What we call empty space, what physicists term the quantum vacuum, is actually alive with invisible activity. Picture the quietest room you've ever been in. Perhaps it's late at night, and you're lying in darkness, listening to what seems like perfect silence. But even in that stillness, if you listen carefully, you might hear the faint hum of electricity in the walls, the distant whisper of wind, the gentle settling of the house around you. The quantum vacuum is like that quiet room, but infinitely more active. At scales smaller than atoms, smaller than anything we can directly perceive, space itself is buzzing with what physicists call virtual particles. These aren't particles in the usual sense, they're quantum fluctuations, brief borrowings of energy from the fabric of space-time itself. Pairs of particles and antiparticles pop into existence from nothing, dance together for the briefest instant, and then annihilate each other, returning their borrowed energy to the void. This isn't speculation or theoretical fancy. These virtual particles have measurable effects on the real world. They slightly alter the energy levels of electrons in atoms, creating tiny shifts in atomic spectra that can be detected with exquisite precision. They generate forces between metal plates placed extremely close together in vacuum, a phenomenon called the Casimir effect, where the quantum foam of empty space actually pushes objects together. The implications are staggering. Nothing, it turns out, is never truly nothing. Even in the deepest regions of intergalactic space, where matter is so sparse that you might encounter only a handful of atoms in a volume the size of a cathedral, the quantum vacuum continues its restless dance. Virtual photons flicker in and out of existence. Virtual electron-positron pairs materialize and vanish, and the very geometry of spacetime trembles with quantum uncertainty. Some physicists even suspect that this quantum activity might be connected to the greatest mystery in modern cosmology: dark energy. The mysterious force that's accelerating the expansion of our universe might emerge from the quantum fluctuations of empty space itself, though the mathematics suggest an energy density that's catastrophically larger than what we observe. It's as if the universe has found some elegant way to balance its quantum books that we don't yet understand. As you rest tonight, consider this: the space between your atoms, the gaps between the molecules in the air you breathe, even the apparent emptiness between distant stars. All of it is alive with quantum possibility. You're not just surrounded by matter and energy in their familiar forms. You're immersed in a sea of potential, a cosmic ocean of virtual events that influence the reality you experience in ways both subtle and profound. There's something almost philosophical about the way quantum mechanics treats the act of knowing itself. In our everyday world, we assume that things have properties whether we observe them or not. A tree falling in an empty forest makes a sound, we believe, even if no one is there to hear it. The moon exists in its orbit, whether we look up at the night sky or not. These seem like reasonable assumptions about the nature of reality. But quantum mechanics suggests something far more subtle and strange. It proposes that at the most fundamental level, particles don't have definite properties until they're measured. Not just unknown properties that we haven't discovered yet, but genuinely indefinite properties that don't exist in any meaningful sense until observation brings them into being. This is the measurement problem, and it's one of the deepest puzzles in all of physics. When we say that a particle is in a superposition of states, we mean that it's not secretly in one state or another, waiting to be revealed. It's in a quantum combination of all possible states, a mathematical entity that encompasses every possibility simultaneously. But then measurement happens. A detector clicks, a photon is absorbed, a quantum state interacts with the macroscopic world, and suddenly the superposition collapses. All those possibilities reduce to a single outcome, and the particle acquires definite properties for the first time. What triggers this collapse? Is it consciousness? Is it simply any interaction with the environment? Is it the irreversible amplification of quantum information into the classical world? Different interpretations of quantum mechanics give different answers, and after nearly a century of debate, physicists still don't agree on which interpretation is correct. Some researchers have proposed that consciousness itself plays a fundamental role in wave function collapse. They suggest that the universe exists in a superposition of all possible states until a conscious observer makes a measurement, at which point reality crystallizes into the specific outcome we experience. It's a romantic notion, placing consciousness at the center of physical reality, making observers active participants in the creation of the universe, rather than passive witnesses to its unfolding. Others argue that consciousness is irrelevant, that any interaction between a quantum system and its environment is sufficient to cause decoherence and apparent collapse. In this view, measurement isn't special because it involves consciousness, but because it involves irreversible information transfer from the quantum realm to the classical world. Still others embrace the many worlds interpretation, suggesting that wave functions never collapse at all. Instead, every possible outcome of every quantum measurement actually occurs, but in separate branches of reality. We experience only one branch, but all the others are equally real, populated by other versions of ourselves who observe different outcomes. The measurement problem isn't just an abstract philosophical puzzle. It touches on fundamental questions about the nature of reality, the role of information in physics, and the relationship between the microscopic quantum world and the macroscopic classical world we inhabit. It asks us to consider whether reality is objective or observer-dependent, whether the universe is deterministic or probabilistic, and whether consciousness is merely an emergent property of complex matter, or something more fundamental to the structure of existence itself. Perhaps nowhere is the strangeness of quantum mechanics more surprising than in its potential role in biological systems. For decades, scientists assumed that the warm, wet, noisy environment of living cells would destroy quantum coherence too quickly for quantum effects to play any meaningful role in biology. Quantum phenomena, they believed, were confined to the sterile conditions of physics laboratories and the vacuum of space. But life, as it so often does, has found ways to surprise us. Consider the European robin, a small bird that navigates vast distances during migration with uncanny precision. How does it know which direction is magnetic north? Recent research suggests that the answer might lie in quantum entanglement. Inside the robin's eye, there may be proteins containing pairs of electrons that become quantum entangled when exposed to light. These entangled electrons interact differently with Earth's magnetic field depending on the bird's orientation, creating a kind of quantum compass that allows the robin to literally see magnetic fields as patterns of light and shadow. If confirmed, this would mean that quantum entanglement, that most ethereal and abstract of quantum phenomena, is being used by living creatures for practical navigation. The same spooky action at a distance that Einstein found so troubling might be guiding birds across continents, helping them find their way home across thousands of miles of open ocean. Or consider photosynthesis, the process by which plants convert sunlight into chemical energy. Classical physics would suggest that when a photon hits a chlorophyll molecule, the energy would hop randomly from molecule to molecule until it reaches a reaction center where it can be stored. This random walk should be inefficient, with much of the energy lost as heat along the way. But measurements of photosynthetic complexes reveal something remarkable. The energy doesn't wander aimlessly. Instead, it appears to explore multiple pathways simultaneously, using quantum coherence to find the most efficient route to the reaction center. It's as if the energy exists in a superposition of all possible paths, then collapses to the optimal one. This quantum efficiency might help explain why photosynthesis is so remarkably effective at capturing and converting solar energy. Plants may have evolved to harness the strange properties of quantum mechanics, using superposition and coherence to optimize their energy harvest in ways that purely classical systems simply cannot match. Even our sense of smell might involve quantum effects. The traditional model suggests that odor molecules fit into receptor proteins like keys into locks, with different shapes producing different smells. But this model has problems. Molecules with similar shapes sometimes smell completely different, while molecules with different shapes can smell identical. An alternative theory proposes that our noses detect the vibrational frequencies of odor molecules through quantum tunneling. When a molecule binds to a receptor, electrons in the receptor might tunnel through the molecule, and the probability of tunneling could depend on how the molecule vibrates. This would allow our olfactory system to distinguish between molecules not just by their shape, but by their quantum mechanical properties. These discoveries suggest that quantum mechanics isn't just the domain of physicists and their exotic experiments. It might be woven into the very fabric of life itself, enabling the processes that make consciousness, perception, and biological complexity possible. We might be quantum creatures living in a quantum universe, our thoughts and sensations emerging from the same strange principles that govern the behavior of subatomic particles. As we near the end of our gentle journey through the quantum realm, it's worth pausing to consider just how much mystery remains. For all our sophisticated mathematics, for all our precision experiments and technological achievements, quantum mechanics still presents us with puzzles that challenge our deepest assumptions about the nature of existence. There's the hard problem of quantum gravity, the seemingly impossible task of reconciling quantum mechanics with Einstein's general relativity. These two theories represent humanity's most successful descriptions of nature, yet they seem fundamentally incompatible. Quantum mechanics describes a universe built from discrete packets of energy and information, while general relativity portrays a smooth, continuous space-time. Somewhere in that incompatibility lies a deeper truth about the universe that we haven't yet grasped. There's the mystery of dark matter and dark energy, which together comprise about 95% of the universe, yet remain completely outside our current understanding of quantum mechanics. Are these phenomena quantum in nature? Do they represent new particles and fields that we haven't yet discovered? Or do they point toward fundamental modifications to our theories of space, time, and matter? There's the question of quantum consciousness, the possibility that the strange properties of quantum mechanics might play essential roles in generating the subjective experience of awareness. Some researchers have proposed that microtubules in brain neurons maintain quantum coherence long enough to influence neural processing, while others suggest that quantum entanglement between different parts of the brain might explain the unified nature of conscious experience. And there's the deepest mystery of all. Why does the universe appear to be quantum mechanical in the first place? Why do particles exist in superpositions? Why does measurement cause wave function collapse? Why do distant particles become entangled? These aren't just technical questions about how quantum mechanics works. They're fundamental questions about why reality has the structure it does. Perhaps the most profound lesson of quantum physics isn't any particular fact or phenomenon, but rather the reminder that reality is under no obligation to conform to our expectations or intuitions. The universe is far stranger, far more subtle, and far more beautiful than our everyday experience would suggest. It operates on principles so alien to our common sense that even after a century of study, they continue to surprise and perplex us. Yet there's something deeply comforting in this strangeness. It suggests that no matter how much we learn, no matter how sophisticated our theories become, there will always be new mysteries to explore, new questions to ask, new wonders to discover. The universe is not just a machine waiting to be completely understood and catalogued. It's an endless source of mystery and beauty, a cosmic poem written in mathematics we're still learning to read. As you drift towards sleep tonight, perhaps you'll find comfort in knowing that you're part of this vast quantum tapestry. The atoms in your body were forged in the hearts of distant stars. The electrons in your neurons are dancing to quantum rhythms, and the very thoughts flowing through your mind might emerge from the same mysterious principles that govern the behavior of particles in the deepest reaches of space. You are not separate from the quantum universe. You are woven into it, a conscious pattern in the cosmic web of possibility and actuality, mystery and revelation. And in your dreams tonight, you might catch glimpses of realities that exist in superposition, of worlds where different quantum outcomes unfold, of the infinite branching tree of possibility that quantum mechanics suggests might be the true structure of existence itself. Music swells gently, then fades to a whisper. The quantum realm has revealed its secrets to us tonight, But there are other mysteries calling from the cosmic darkness. What if space itself has boundaries? What if there are edges to existence where everything simply ends? Join me next time as we explore the ultimate question about the nature of the cosmos in Does Space End? Sleep documentary. Until then, rest well in the knowledge that reality is far more wonderful and strange than we ever dared imagine. Sweet quantum dreams, fellow explorers. The universe is dreaming too, and in its dreams, all possibilities coexist in perfect, shimmering harmony. There's a question that has haunted philosophers and scientists alike for centuries, one that quantum mechanics has made both more urgent and more mysterious. What is consciousness, and where does it come from? As you rest tonight, listening to these words, something extraordinary is happening inside your skull. Billions of neurons are firing in intricate patterns. Electrical impulses are cascading through networks of unimaginable complexity. And somehow, from this biological machinery emerges the vivid, immediate experience of being you. But here's what makes this even more profound. Some of the most cutting-edge research in neuroscience suggests that consciousness itself might be fundamentally quantum mechanical in nature. Consider what happens when you become aware of a thought, when an idea suddenly crystallizes in your mind from the fuzzy background of mental noise. One moment, the thought doesn't exist in any meaningful sense. The next, it's there, clear and present in your awareness. This transition from potential to actual, from possibility to reality, bears a striking resemblance to quantum wave function collapse. Dr. Roger Penrose, the brilliant physicist and mathematician, has proposed that consciousness emerges from quantum processes occurring within the microtubules of brain cells. These tiny structures, smaller than anything visible under ordinary microscopes, might maintain quantum coherence even in the warm, wet environment of living tissue. According to this theory, consciousness isn't simply an emergent property of complex neural networks. It's a quantum phenomenon arising from the same strange principles that govern the behavior of particles in physics laboratories. Imagine that each moment of conscious awareness corresponds to a quantum measurement event, a collapse of possibilities into a single experienced reality. Your thoughts wouldn't be deterministic outputs of a biological computer, but rather quantum selections from a vast space of potential mental states. This would mean that consciousness has genuine agency, that the choices you make and the thoughts you think emerge from quantum indeterminacy rather than strict causal chains. Recent experiments have begun to probe these possibilities. Researchers have detected quantum-like effects in biological systems, from the quantum coherence in photosynthesis to the possibility of quantum entanglement in bird navigation. Some studies have even suggested that anesthetics might work by disrupting quantum processes in brain microtubules, literally switching off the quantum basis of consciousness. If these ideas prove correct, they would revolutionize our understanding of what it means to be conscious, to think, to experience the world. They would suggest that your awareness right now, as you process these words and form responses to them, represents a quantum interface between your physical brain and the deeper structures of reality itself. But whether consciousness is quantum or classical, one thing remains certain. It emerges from the same atoms, the same particles, the same fundamental forces that govern everything else in the universe. The boundary between mind and matter, between observer and observed, becomes increasingly blurry the deeper we probe into the nature of existence. In the heart of laboratories around the world, a revolution is quietly unfolding. Scientists are learning to harness the strangeness of quantum mechanics, not just for abstract understanding, but for practical technologies that could transform civilization itself. This is the dawn of the quantum information age, and its implications reach far beyond anything we might have imagined. Quantum computers represent perhaps the most dramatic example of this transformation. Unlike the digital devices that surround us, which process information as definite bits that are either 0 or 1, quantum computers manipulate quantum bits, or qubits, that can exist in superpositions of both states simultaneously. This isn't just a minor technical improvement. It's a fundamental reimagining of what computation means. A classical computer exploring a maze would try each path one at a time, systematically working through possibilities until it found the exit. A quantum computer could explore all paths simultaneously, using the parallel processing power of superposition to solve certain problems exponentially faster than any classical approach. This has profound implications for cryptography and security. Many of the encryption methods that protect our digital communications rely on the difficulty of factoring large numbers, a task that would take classical computers centuries to accomplish. But a sufficiently powerful quantum computer could break these codes in hours or days, rendering much of our current digital security obsolete. Yet quantum mechanics also offers solutions to the problems it creates. Quantum cryptography uses the fundamental properties of quantum mechanics to create communication systems that are theoretically unbreakable. Any attempt to eavesdrop on a quantum encrypted message necessarily disturbs the quantum states being transmitted, immediately alerting the legitimate users to the security breach. The implications extend far beyond computing and communication. Quantum sensors can detect gravitational waves from colliding black holes, measure magnetic fields with unprecedented precision, and potentially even probe the quantum structure of spacetime itself. Quantum simulators might help us understand complex materials, design new drugs, or model the behavior of biological systems at the molecular level. But perhaps the most profound impact of quantum technologies won't be on our external world, but on our understanding of ourselves and our place in the universe. These devices don't just use quantum mechanics as a tool, they make its strangeness tangible, bringing the abstract mathematics of wave functions and superpositions into the realm of everyday experience. When you interact with a quantum computer, you're not just using a fast calculator, you're engaging with a machine that embodies the deepest mysteries of existence, a device that operates according to principles that challenge our most basic assumptions about reality. In a very real sense, these technologies are making philosophers of us all, forcing us to confront questions about the nature of information, measurement, and consciousness that have puzzled thinkers for generations. As we venture deeper into the quantum realm, we encounter one of the most ambitious projects in all of physics. The attempt to understand how quantum mechanics fits together with gravity and the structure of spacetime itself. This quest for a theory of quantum gravity represents not just a technical challenge, but a journey toward the most fundamental description of reality that physics can provide. Einstein's general relativity paints a picture of spacetime as a smooth, continuous fabric that can be curved and warped by the presence of matter and energy. Massive objects like stars and planets create depressions in this fabric, and the motion of other objects through these curved regions is what we experience as gravity. It's an elegant, geometric vision of the universe that has passed every experimental test for more than a century. But quantum mechanics suggests that at the smallest scales, this smooth picture must break down. Just as matter and energy come in discrete quantum packages, space-time itself might be granular, built from tiny, indivisible units of space and time. At scales trillions of times smaller than a proton, the smooth fabric of Einstein's relativity might give way to a quantum foam, a churning sea of virtual black holes, wormholes, and space-time fluctuations. This quantum structure of spacetime might help resolve some of the deepest paradoxes in physics. Black holes, for instance, appear to destroy information when they evaporate through Hawking radiation, violating one of the fundamental principles of quantum mechanics. But if space-time itself is quantum mechanical, there might be subtle ways for information to escape from black holes, preserved in the quantum correlations between the radiation they emit and their shrinking event horizons. String theory proposes that the fundamental constituents of reality aren't particles at all, but tiny vibrating strings existing in multiple dimensions beyond the three spatial dimensions we experience. These strings would generate all the particles and forces we observe through their different vibrational modes, like cosmic musical instruments playing the symphony of existence. Loop quantum gravity takes a different approach, suggesting that space itself is woven from discrete loops and networks of quantum geometry. In this picture, space-time emerges from more fundamental quantum relationships, like a tapestry arising from the interweaving of individual threads. Both approaches remain highly speculative, requiring mathematical tools and conceptual frameworks that push the boundaries of human understanding. Yet they represent humanity's most ambitious attempt to answer the ultimate questions about the nature of existence. What is space? What is time? How does the quantum world give rise to the classical reality we experience? As you rest tonight, consider that the space around your body, the time through which your thoughts flow, might themselves be quantum phenomena. The distance between your hand and the wall, the duration of your breath, the flow of moments from past to future, all of this might emerge from quantum processes occurring at scales so small that they make atoms seem like galaxies. Our journey through quantum strangeness has taken us from the smallest scales of existence to the largest. And now we find ourselves contemplating how quantum mechanics might shape the entire cosmos. The universe itself, it seems, bears the fingerprints of quantum processes that occurred in its earliest moments, traces of quantum behavior written across the cosmic microwave background and embedded in the large-scale structure of galaxies and galaxy clusters. In the first fraction of a second after the Big Bang, when the universe was smaller than a proton and hotter than the core of any star, quantum fluctuations in the fabric of space-time itself might have been stretched by cosmic inflation into the seeds of everything we see today. Those tiny quantum variations, amplified to astronomical proportions, could have determined where galaxies would form, where stars would ignite, and ultimately where planets like Earth would emerge. This means that the quantum uncertainty principle, operating at microscopic scales during the universe's infancy, might be responsible for the cosmic web of matter that stretches across billions of light years. The same principle that prevents us from knowing both the position and momentum of a single particle with perfect precision might have shaped the distribution of matter and energy throughout the entire observable universe. Dark matter, that mysterious substance that outweighs ordinary matter by a factor of 5 to 1, might itself be composed of exotic quantum particles that interact only weakly with the matter we know. These particles could be relics from the early universe, quantum excitations that have survived for nearly 14 billion years, invisible to our telescopes but detectable through their gravitational influence on visible matter. Dark energy, the even more mysterious force that's accelerating the expansion of the universe, might emerge from the quantum vacuum itself. The empty space between galaxies isn't truly empty, but filled with quantum fields that fluctuate even in the absence of particles. Some theories suggest that these quantum fluctuations could generate a kind of cosmic pressure that pushes space apart, driving the accelerated expansion we observe. If these ideas prove correct, they would represent the ultimate triumph of quantum mechanics, demonstrating that the strange principles discovered in early 20th century physics laboratories govern not just atoms and molecules, but the behavior and evolution of the entire cosmos. The same mathematics that describes the behavior of electrons in atoms would also describe the fate of the universe itself. This cosmic perspective on quantum mechanics offers a profound kind of comfort. It suggests that the strangeness we find so puzzling and counterintuitive isn't a bug in the universe's design, but a fundamental feature. The quantum world isn't separate from our everyday experience, alien and incomprehensible. It's the foundation upon which everything else is built, the deep structure that makes stars shine, planets form, life emerge, and consciousness arise. As our exploration of quantum mechanics draws toward a gentle close, we find ourselves face to face with questions that transcend physics and enter the realm of philosophy. What does quantum mechanics tell us about the nature of reality itself? Are we passive observers of an objective universe or active participants in its creation? Is there a single definite reality underlying our observations, or do we live in a world of irreducible possibilities and probabilities? Different interpretations of quantum mechanics offer radically different answers to these questions. The Copenhagen interpretation, favoured by many of the theory's founders, suggests that quantum mechanics is complete as it stands, that particles really don't have definite properties until they're measured, and that asking what's really happening before measurement is meaningless. In this view, reality is fundamentally observer-dependent, emerging from the interaction between quantum systems and classical measuring devices. The many-worlds interpretation takes the opposite approach, suggesting that reality is far larger than we experience. Every quantum measurement causes the universe to split into multiple branches, each corresponding to a different outcome. We experience only one branch, but all the others are equally real, populated by other versions of ourselves who observed different results. In this interpretation, reality is objective and deterministic, but vastly larger than our limited perspective reveals. Hidden variable theories propose that quantum mechanics is incomplete, that there are deeper levels of reality we haven't yet discovered. These theories suggest that particles do have definite properties at all times, but these properties are influenced by subtle, non-local connections that create the appearance of quantum randomness and correlation. Each interpretation carries profound implications for how we understand ourselves and our place in the universe. Are we unique conscious beings in a single reality, or are there countless versions of us experiencing parallel quantum histories? Do our choices and observations literally create the reality we experience, or do they simply select which branch of a pre-existing multiverse we find ourselves in? Perhaps the most profound insight from quantum mechanics isn't any particular answer to these questions, but rather the reminder that reality might be far more subtle, complex, and beautiful than our everyday intuitions suggest. The universe doesn't have to conform to our expectations or make sense according to our common sense notions of how things should work. This quantum perspective offers a kind of intellectual humility that's both challenging and liberating. It suggests that no matter how much we learn about the universe, there will always be deeper mysteries to explore, stranger phenomena to discover, and more profound questions to ask. The more we understand about quantum mechanics, the more we realize how much we don't understand about the fundamental nature of existence. Yet there's also something deeply satisfying about this endless mystery. It means that the universe is not a closed book waiting to be completely read and understood, but an open-ended conversation between human curiosity and cosmic possibility. Each answer we discover opens up new questions. Each mystery we solve reveals deeper mysteries, and each step forward in our understanding brings us face to face with the beautiful, inexhaustible complexity of existence itself. As you drift towards sleep tonight, perhaps you'll find yourself wondering about the quantum processes occurring in your own brain, the superpositions collapsing into conscious thoughts, the entangled states that might connect your awareness to the broader structures of reality. You might dream of parallel selves making different choices in other quantum branches, or of virtual particles dancing in the empty spaces between your atoms. These aren't just abstract speculations or mathematical curiosities. They're invitations to see yourself and your world with fresh eyes, to recognize the profound mystery and beauty that surrounds us at every moment. You are not separate from the quantum universe we've explored tonight. You are one of its most remarkable expressions, a conscious pattern in the cosmic web of possibility and actuality. The quantum realm has shared its deepest secrets with us, revealing a universe far stranger and more wonderful than we ever dared imagine. But our cosmic journey is far from over. There are other mysteries calling from the depths of space and time, other questions that probe the very foundations of existence itself. What if everything we think we know about space is wrong? What if the universe has boundaries, edges where existence itself comes to an end? What if there are realms beyond the reach of light, matter, and even mathematics itself? Join me next time as we explore the ultimate cosmic mystery in double-slit. Does space end? Sleep documentary, where we'll venture to the very limits of the known universe and peer into the abyss of infinite possibility. Until then, rest well in the quantum embrace of uncertainty and wonder. The universe is dreaming alongside you, and in its dreams, all possibilities dance together in perfect eternal harmony. Sweet dreams, fellow quantum explorers. Reality awaits your next observation. And so we find ourselves at the end of this quantum odyssey, having journeyed from the familiar world of classical physics into realms where reality itself becomes fluid, uncertain, and beautifully strange. We've witnessed particles that dance through multiple states simultaneously, explored the spooky connections that bind distant objects across the cosmos, and contemplated the possibility that consciousness itself might emerge from quantum processes occurring in the depths of our minds. What have we learned from this gentle exploration? Perhaps the most profound lesson is that the universe is under no obligation to match our expectations. The reality revealed by quantum mechanics is far more subtle, more interconnected, and more mysterious than our everyday experience would suggest. Yet in this strangeness lies a kind of poetry, a reminder that existence itself is more wonderful than we ever dared imagine. From wave-particle duality to quantum entanglement, from tunneling electrons to the measurement paradox, each phenomenon we've encountered challenges us to expand our understanding of what it means for something to exist. The quantum realm doesn't offer simple answers or comfortable certainties. Instead, it presents us with a reality that shimmers between possibility and actuality, where observation and reality dance together in ways that continue to puzzle the brightest minds in physics. As you rest tonight, carry with you this quantum perspective on existence. Remember that you are not merely a collection of atoms following predictable paths through space and time. You are a conscious observer in a universe where the very act of observation participates in creating reality. The thoughts flowing through your mind as you drift towards sleep might themselves emerge from quantum processes, your dreams unfolding through the same mysterious principles that govern the behavior of photons and electrons. The quantum universe we've explored together reveals that mystery isn't the enemy of knowledge, but its most intimate companion. Each answer quantum mechanics provides opens new questions, each discovery reveals deeper puzzles, and each step forward in our understanding brings us face to face with the infinite complexity and beauty of existence itself. This is perhaps quantum mechanics' greatest gift, not certainty, but wonder. Not final answers, but an endless invitation to explore, to question, to marvel at the strangeness and beauty of the cosmos we call home. In a universe where particles can exist in multiple states simultaneously, where distant objects share instantaneous connections, and where the act of measurement shapes reality itself, there is always more to discover, always deeper mysteries waiting to unfold. Sweet dreams, fellow quantum travelers. Rest well in the knowledge that reality is far more extraordinary than we ever imagined, and that tomorrow brings new opportunities to explore the endless mysteries that surround us. The universe is dreaming alongside you, and in those dreams, all possibilities exist in perfect, shimmering superposition. Shimmering superposition.